Hello everyone and welcome to another video. So today I want to continue our discussion on bang bang control by making a small modification to that control algorithm by adding a hysteresis deadband. So if you remember in our previous video, right, we discussed what is bang bang control. It was a really simple closed loop control system which had some pros and some cons, and we'd like to ameliorate some of those cons with this hysteresis deadband. So just to refresh your memory, right, we said you've got a plant, you've got a controller. Last time we looked at the really simple bang bang controller, right, which all this thing did was basically turn the controller on, bang onto one stop when a certain condition happened, and then it turned it bang off to another stop if the else statement effectively occurred, right? So this on-off logic that was occurring, it was really one if statement that we saw earlier, right? And the case that we are going to continue investigating is, let's continue considering our thermal system, right, where we basically have a heater. So the actual output is a temperature, and the commanded is some desired temperature that we would like this heating system to achieve. And what the system is going to do, this bang bang controller or the bang bang with the hysteresis deadband, is it's just going to vary the duty cycle of the heater between a 0 and 1. So 0 meaning off, 1 meaning completely on. Or what we saw last time is you can change this U on parameter. So it doesn't have to be on, bang on at 1. You could have this at 80%, 70%, 50%, whatever you want. But basically, you're just defining what are the stops of the maximum U and the minimum U for the bang bang part of the controller, right? So we said the logic was exceedingly simple, right? We said that if the sign of your error was positive, you turn the thing on, because in this case you're too cold, you want to turn the heater on. Otherwise, you're probably too hot, just turn the heater off. So this output is either a 1 or a 0, right? We talked about this last time. This is a 1 or a 0. And then when you multiply it by U on, you basically get the bang bang scheme of your controller, right? And we said this worked great in a nice, perfect system, right? The thing starts off too cold, you're trying to reach some set point T desired, and the error starts out positive, and then it starts going down, 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 down. And during this time, while you're warming up, right, the heater is on at the U on value. But then as soon as you flip over to the negative error, right, you basically overshoot. So now you're too hot, right? So up here, you're too hot. So you turn the heater off, right? And again, we talked about this in our last video, so I'm going over this very quickly. What I think is interesting, right, is we saw the problem with this system, right, comes from the fact that what if there's noise on top of this signal, right? If this is a real world system, you're actually measuring the temperature using something like a thermocouple or some other sensor, right? There's going to be noise on this signal, right? So this is going to be something like this, right? And down here it's no problem, but as soon as you start getting close to the set point, right? If you have a noisy measurement that bumps you above the value, and then the very next second it bumps you below the desired value, right? What that means for your error is that the error flip-flops like this, right? So your control signal is going to flip-flop, right? And we get this chattering effect, right? We talked about this last time, okay? So this chattering, if you think about this long enough, it comes from the fact that you've got this noise which is rapidly bouncing you positive error, negative error, positive error, negative error, positive error, negative error, right? The controller, it's being wishy-washy, right? It just hasn't committed one way or another. That's why you get this chattering, right? It's like, oh, I don't know, I want to turn it on, turn it off, turn it on, turn it off, right? Because the noise is bumping you above and below the 0 error line, right? That's kind of what's going on, right? So in effect, what's going on, I guess we could call this, the problem with this bang bang controller is that it's wishy-washy. If that's the technical term for it, right? It just can't make up its mind. It's flip-flopping back and forth. So to fix that, let's add what's known as a hysteresis deadband, okay? So this idea, it's actually pretty cool, and it's not that complicated, okay? So what we're going to do now is we are going to say, all right, fine, you want some desired temperature or just some desired set point. Well, what we're going to do now is let's add, tell you what, for now, let me get rid of all this chattering behavior because I want to redraw this in just a second. Let me erase some of this just to get us a little bit cleaner picture. So let me erase this control signal. Okay, let me erase some of this noise. I'll just try to quickly redraw this picture because we'll re-add the noise in just a second. I just want to make this a little bit cleaner, okay? But the idea now is, okay, fine. We are going to try to get rid of this wishy-washiness. So what we're going to do is we are going to add this deadband. So around the desired set point, what we're going to do is just add a little bit of margin above. Okay, so I'm going to draw something like this. And a little bit of margin below. Okay? And the size of this deadband is it's a controller parameter. So let's call this distance here. This is the deadband size. And in our case, I guess it's a value of degrees Celsius, right? Okay? So you get some deadband here. That also means that we're going to have a little bit of a deadband around the error signal down here of the same magnitude. So let's again draw this like such, right? So you got this deadband like this, okay? And what we're going to do is we're going to take different actions if you're inside the band or outside the band or somewhere in between, okay? So again, this here is your deadband size. And again, to maybe avoid having to keep writing this out over and over and over, let's just go ahead and I'll say you need one more controller parameter. Let's call it maybe like alpha. This is like your deadband size. Okay, so you have basically right up here, this is the value of positive alpha, right? Down here is the value of negative alpha. Okay, so we've got some deadband. Okay? Now, what we're going to do with this deadband is we're going to examine, we're going to do different things depending on where you are relative to this deadband. So, if you look at this long enough, okay, way up here, from positive alpha to positive infinity on the error, what's going on here? In that case, you are basically, it's like way too cold. You're down here, right? You're not even close to the deadband. So out here, you definitely want the heater on. Right? There's no question about it, right? In this region up here, because you're let's call it like way too cold. Okay? Similarly, in this section down here, where you are in the negative alpha to negative infinity, you basically definitely want the heater off, right? Because you're way too hot, right? Because down here, is when you're up here, right? When your actual signal is way above your desired set point, yielding you this way negative value, right? Okay? Now, where it gets interesting is what do you do when you're inside the deadband? When the error signal is inside the deadband, in this case, we are going to say that the heater state, it's going to vary or depend on conditions. Okay? And again, I'm trying to draw all this nicely on the board, but if you want a nice picture here, go ahead and download the lecture notes. Again, look at the description of this video. There's a link to a GitHub page with lecture notes, and as well as a lot of the code that we're going to be building here in a second. But feel free to download that now if you'd like to kind of follow along. Okay, so let's think about this. What do we want to have happen? Okay, let's look at this picture. And maybe what we can do is let's draw a couple of vertical lines that might help us see what's going on. So we are very interested in something, what would happen right here? Like let's say when you first enter this deadband, like this. Okay? And then there's another kind of critical point where out here, oops, sorry, sorry, wait, sorry. To be consistent with my notes, I want to move this actually over. Sorry, this line. We actually want to look at the case where you first exit the deadband. Sorry. Let me move this over just a skosh. I actually want this one right here, where you first exit the deadband. And you're going to see why in just a second. So that goes through this point. There we go. Okay. And then what we're going to want to look at is this point right here. Okay. And you're going to see why in just a second. Okay, and then here's another one of these cycles right over here. And I think those are the three critical points we have on this picture, okay? Okay? All right, so what's going on is, let's look at this. You're down here, okay? You are way too cold. So you definitely want the heater on. So the heater's going to be on. Now, the question is, what happens right here when you first enter this deadband? So let me draw this line over to here maybe, right? So I'm not quite to my little critical point, but we are basically, we're on this downswing now, right? So you've entered into the deadband, okay? And the question is, what do you want to do right here? So let me maybe put a little green for comment. What you want to think about doing right here is, we're trying to avoid this wishy-washy problem, okay? So the heater is on, right? The heater's on out here. You're heating up, heating up, heating up, heating up. Now, inside this band, what you're going to want to do is, we are going to want to allow the system to stay on until we completely pass through this deadband. We're going to commit. We're going to fully commit. It's like go big or go home. It's just, you are going to stay on until you completely pass through this deadband, okay? You're not going to change the state of the control to avoid this chattering, right? So what we're doing in this downswing is, you want to leave on until you pass completely through the deadband, okay? So we've committed, okay? So what that means for your control signal is, it's on, okay? There we go. Now, at this point here, this is where we drew the first vertical line, okay? Now you have completely passed through the other side of the deadband, right? You came through here, 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 and you're outside. Now, you're way too hot, right? You're way too hot up here. So now we are going to make a change. As soon as you completely pass through the deadband, that's when we're going to turn off, okay? Okay, and then same thing, we're just going to keep on going, okay? So now outside, right here is where you turn off, okay? And you stay off, 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 and now we got another decision point to make, right? You enter back into the deadband, right? Because it's off, you're cooling down, you're cooling down, you're cooling down, you're cooling down, you're cooling, and now you enter the deadband. And again, we're going to do the same thing. Avoid the wishy-washiness. You're going to commit. You are not going to change the state of the heater until you pass completely through the deadband. So right here, when we are on the upswing in error, right? This is when you're cooling, right? So we're cooling, and we're going to commit to cooling down until you get all the way through. So this part right here is, again, we are going to leave in the off state until we pass completely through the deadband. Okay? So down here, again, you can think about this. This is like the cooling cycle, and over here was the heating cycle, right? But again, what we're doing now is, okay, you're going to stay, whoopsies, you're going to stay cooling, 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 until you reach this point here, where now you've made it, the error has left the deadband completely, right? And now, that's when we switch back on. Okay? Yep. And basically, yeah, we just repeat this pattern. I think everyone sees what's going on at this point, right? So now we do the same thing. So the heater is, it turned on right here, right? As soon as you pass out, this is where it goes on. And we stay on, and again, you enter the deadband, and we commit. We commit to heating all the way through, so it's still on, until you leave the deadband completely out here. So you get this, right? So that's the algorithm, and now if you think about this long enough, you can kind of see why this helps with the chattering problem. Because again, if we add the noise back on top of this signal, right? We say, okay, fine, this is now noisy, 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 noisy. And again, error signal is therefore noisy, 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 noisy. Let's think about this real closely, what's going on right about here. Okay, so again, you are outside the deadband, you're on. But the noise bumps you back into this deadband, right? So you are on at this sample, and again, you stay on, even though you're out here, right? You're on, okay? Now, say the noise bumps you out again out here, outside the deadband. Well, heck, you're still on. So even though you've bumped in and out, and maybe you are chattering in and out of the deadband, notice that it's on to on to on to on, is chatter on. So really, there's no chatter from the control signal, it stays on, right? So it's gonna keep going now, and now if you're noisy, it's still on. Now, let's say you're right here, okay? You're about to leave the deadband, right? So the heater is on, right? So let's say the noise bumps you outside, okay? Now you've left. Now you turn the heater off, right? But you commit to being off. So even if the noise bumps you back into the deadband, you stay off, right? Because we're not going to flip the heater back on until you reach the complete other side of the deadband. So as long as this deadband is wider than, say, your noise profile or your noise power, this noise or this thing that might bump you in and out of the deadband isn't going to matter, right? So that's why this works. So let's think about how are we going to implement this. Again, I apologize, this picture got dirty kind of quickly, but check out the lecture notes. The behavior is pretty simple. So all we're going to have to do is, let's come back over here and modify our system here. So let's not go with this wishy-washy bang-bang controller. Let's change this to a bang-bang controller with the Hysteresis Deadband. Okay, so we see that what we're going to have to add is we need this alpha parameter, or the deadband size, right? This is one more controller parameter that needs to come into this. So we're going to actually have to have the deadband size input to the controller, okay? Now, this on-off logic, we got to think about this, right? The on-off, you see, you're on until you go into the deadband, then you got to commit, then you're off, and then you commit, and then you're, right, you flip-flop, but we need more information, right? So what's going on is we actually can think about this as, let's modify our if statement. So again, this thing, we need to now pass it one more parameter, right? In addition to the error, we also need the deadband size. And maybe I'm going to call this alpha just to avoid having to write that, right? Alpha is just the size of your deadband, okay? So now, okay, if your error is greater than, not 0 in this case, right? Now we got to modify this, because now what we're talking about is if your error is bigger than alpha, right? Where are you? That's this situation when the error is bigger than alpha, it's way too cold. So the heater is going to be on. So that's fine. Let's leave this statement right here. It's too cold. In fact, let's add a little note. It's way too cold. Right? Leave the heater on. Okay? Else, let's change this to an else if. Else if, what if your error is less than negative alpha? Right? That's down here. Right? This is now when you're way too hot. So again, let's modify our little comment here. It's not just too hot, it's way too hot. So again, you turn the heater off. Right? That's great. Okay? Now, let's modify this. Let's say if the else, okay, so now else. The only other thing that could happen now is now we need some logic for what to do when you're in the deadband. So now we're in the deadband. Okay? So there's a couple things that you can do. Okay? What we can do is, let's come back to our picture. As much as we can do this with, let me see if I can clean this up. I mean, the noise is getting in our way and it's kind of making this discussion a little bit more complicated. Let me see if I can just quickly redraw and touch this up to make this a little bit cleaner so we can talk about this a little bit more easily. Okay, let's look at this first transition, okay? So we said you're definitely on. You're on, right? Okay? And then, yeah, okay, then you flip it to off. Right? Once you pass outside, okay, you're off. Now, here's where we probably want to think about what we're going to want to do, right? We enter into this deadband, okay? Right here, the sample before, you were off, okay? Now notice, as soon as you enter in the deadband, what you still want to do is, we've committed to cooling, so you still want to stay off, okay? And similarly, that's the similar situation over here, right? Over here, you were on outside the deadband. the next sample, the next time step forward, you enter into the deadband, but what we want to do is we want to stay committed to heating, right? So you want to stay on. So really, what this is doing, if you think about this long enough, is we actually need to remember what we were doing one time step before, because that will tell us what we do at the current time step when we first enter into the deadband, okay? So if you look at this long enough, you can see, oh, okay, if the time step before, so I am examining the second I get into the deadband, okay? In order to know what I should do, I should look at one time step previous and see what I was doing. So when I enter the deadband, if I was off, stay off. The second you enter the deadband, if you were on, stay on. That's what's going on. So really, what we should do is we actually need to remember what we were doing one time step before. So let's label this signal, maybe this is G at time K, okay? Now what we're going to do is we actually need to remember or store in memory. I'm going to draw this as a memory block, okay? So I'm going to draw it like this because, spoiler alert, this is what Simulink does, and we're going to look at this in a second. Memory. What this thing does is you give it a signal. It will hold that value that you give it at the current time step for one frame and then output it the next frame. So basically, you get this. So this memory block, it's going to tell you what happened or what this signal looked like one time step in the past. That's great because that's exactly what we need for this logic. So I need to now feed this over here to this function. So this on-off logic, now it actually needs one more piece of information, not just the deadband size, but we also need to know what you were doing. Let's call it GKM1 for GK minus 1. What were you doing one time step before? Now, this is going to allow us to figure out what we do here in the deadband. So here, what you can say is, well, if GK minus 1 was 0, just leave it off, right? So the GK is just going to be 0, right? Else, you must be in the other situation. There's no other way. GK minus 1 is either 1 or 0. So now you're going to say this is just 1. And then end, and then crud. I need one more end statement. I ran out of space. You get what I'm saying. And we're going to look at the code here in just a second in a lot cleaner fashion, right? So this now should hopefully implement this deadband scheme. It should keep track of, are you on the downswing or on the upswing? What are you doing? It's going to commit to one state of your control or not, and we should be good to go. So yeah, that's what this looks like. You know what? Before we leave to look at this in Simulink, I want to investigate one other thing with this. There's another way you can implement this logic in maybe a little bit more intuitive fashion. Okay, so if you think about this whole logic that we're discussing, really the controller, it can be in, there's 4 different discrete states that it can be in, right? You're either way too cold and you turn the heater on, you're either way too hot, so you turn the heater off, and then inside the deadband, there's 2 states. You're either on the downswing or the upswing for warming or cooling, respectively, right? So there's 4 states. So really, what I would like to do is you can actually think about encapsulating this purple box, right? All of this was capturing this logic, right, of those 4 different states. And here's the kind of if-then-else statements that would get you that behavior of how you're transitioning around all these states, right? Well, the other way that maybe we can visualize this is using what's known as a finite state machine, or sometimes people refer to it as a discrete event system or a chart. Any of these terminologies is fine. In fact, we have dedicated discussions on finite state machines and discrete event systems, but I just want to give you a quick example of how we can implement this bang controller with Hysteresis Deadband using a finite state machine. So let's take this purple box like this, right? And I just want to replace all this if then else in the memory block and all that stuff, because you can kind of see how this could get difficult to visualize if the logic got a little bit more complicated. So the equivalent way that we can represent this purple logic is, like I said, let's just enumerate these 4 states. So you can either be way too cold outside the deadband, so that's where we started off out here, right? You're way too cold, so you want to turn the heater on. Okay, now what's the next state that this system can transition to? You can go on down here, and then you could enter into the deadband and be on the warming side, right? You could be, you can continue and commit to warming. What triggers that transition from out here to in here? Well, you can see that's when you cross this threshold of positive alpha. So what we can do is we can draw this like such that if, I'm going to draw an event, that if your error is less than or equal to alpha, right? You now enter into the deadband, and now you're in the warming state. So that's this state right down here, okay? And again, we said we're going to leave this on. And again, you could, again, from the noise discussion, noise could bump you back out here, right? Noise could, at the next very instant, pop you out here. So actually, you could go back to here, okay? So what could happen is you could transition back this way if this was greater than alpha, right? That would be fine, okay? And again, the reason it's fine is you can see it doesn't matter if you rapidly bump between these two states. If you're chattering between these two states, you know, you're right here on the line and you're going bump, 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 bump. It doesn't matter because it's on. You're sending the same control signal to your actuator, so it's going to be totally fine, right? Okay, so anyway, you're in here, you're in here, you're in here. Now what we're going to say is we're going to only allow a transition now to the way too hot state. Okay, so that occurs right here, right? When the error signal goes below negative alpha. So I'm going to draw it like this. I'm going to say, okay, like this. When the error signal is less than minus alpha, right? You transition to here. And this is what's going to save our bacon is we are not going to allow a transition back. So if you bump back over here, we're going to say, forget it. Don't go back to, don't turn the heater back on. So we are not going to draw a line going back here. This is sort of your one-way commit. It's only going to allow an event to get you from this state to this state. You cannot directly go back, right? And therefore, we're going to avoid the chattering, okay? All right, so now you are way too hot outside the deadband. Blah, 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 blah. You're over here. And then again, we're right here. You could bump yourself now into the deadband on the cooling side. So again, we can just say, all right, we're going to allow a transition to go from here to here, right? And this occurs when your error signal, what is it? It's greater than or equal to minus alpha. Okay? And again, for giggles, we could allow ourselves a transition back, okay? When your error signal is less than minus alpha, you could go back here. So we're going to allow chattering between here, but that's not going to matter because when you're inside this deadband and on the cooling side, you're going to stay off. When you're way too hot, you stay off. So again, who cares if you're chattering between off and off and off and off and off? Actuator doesn't care, right? But now, you're cooling until you get to here, okay? Now the second that you go from here to here, that's when we flip to the on state, right? So that means we go from here inside the deadband to cooling, and we go over here, right? To being way too cold and you're outside of the deadband. This occurs, right, when your error signal, right, is greater than alpha. Right? That's when you leave. So you can see around and around this finite state machine we go. So you go here, you could potentially, noise could bump you back and forth here, but eventually you're going to transition to here, and then same thing, you're going to eventually get inside the deadband, maybe outside the deadband, bump, bump, bump. But again, do you see what this is doing, right? This is hopefully going to fix this chattering problem, and this representation is the equivalent of these if-else statements with this on-off logic in the memory block. And again, I just like this finite state machine representation a lot more. I think it's more intuitive. I can understand it a little bit better. And the fun thing is, we're going to see in just a second that Simulink has a nice package that's going to allow us to directly implement this kind of logic within your Simulink model. So with that being said, I think what we should do now is, I think we've got all the logic down. Yeah, we've got all the ideas down. Let's just go over to MATLAB Simulink and build a simulation of this to just verify that this all checks out. Alright, so here's the Simulink model that I've built. It's basically the exact same Simulink model that we looked at last time when we were looking at our simple bang bang system. Although the one addition that I have made is here in the plant model. So earlier we had this plant model. I think I showed you this last video. It was a really simple transfer function model with a little bit of a time delay. But this was a kind of perfect noiseless plant, right? Where it would heat up, it would cool down, it would just take a little bit of time, there would be a little bit of time delay, etc., etc. But it was perfect. So all I've done now is just added a little bit of noise on top of this to simulate a noisy sensor. And we can change this parameter of how much noise or how bad or good is our sensor at will as part of this simulation. So this plant now, it's basically the same thermal system, but it's got a little bit of noise added on top of it because, as we saw, that's what the important part, that's what this hysteresis band is trying to fix, is problems that we encounter due to the noise. Now, the control system right here is I've actually stacked up 3 different controllers, and you can choose which controller we're going to use based on this selection. There's different better ways to do this. I just wanted to do this something simple that we can all easily see and understand. You could get fancy with things like variant subsystems, but that's a discussion for another day. Let's just leave it like this. Again, the first thing we're going to look at is, you could have your really simple bang bang controller. This is what we had last video, right? And we suspect this is going to not do so well with the noise. Or you could have these bang bang controllers with a hysteresis band. So this is the first one we drew on the board, which has the logic that we discussed earlier. Right, it's got this on-off logic where you depend and you change your behavior based on if you're inside or outside the deadband. And then we have this memory block to kind of keep it track of what you were doing last time, right? So this is one way you could implement this. And then the other controller is the Stateflow representation, or the finite state machine. So you can see I replaced that logic with basically the picture we drew on the board. And hang around for a little bit. I'm going to run through the simulations first just so we can see the behavior, but then I will show you how to build this from scratch, because I know Stateflow is a little bit new to potentially some people. This is another package within Simulink that's going to allow us to build these finite state machines nice and clean. You can even see it's kind of colored differently, it's drawn differently as sort of these rounded edges. It's called a chart. But again, I just wanted to point that out, that theoretically these two are the same thing. These are both the bang bang controller with the hysteresis deadband. So let's start off with this. Let's just run this first bang bang controller with our noisy plant just so we can illustrate the problem. So I've set it up so that the bang bang controller is in the loop right now. So if I run this and we come look at this scope, we can see all of the different parameters. So as we saw, in fact, let me zoom this in so maybe it makes it a little bit easier to see. So yeah, we've got a little bit of a noisy plant. In fact, if you zoom in, and let me zoom in just a second, but you'll see there is some chatter going on. It's achieving the temperatures, but if we look closer, like into here, yeah, you can see the noise on top of the signal. And again, I chose the amount of noise to represent something reasonable to our real physical system that we're going to look at in just a couple of minutes. But you can see, here's the problem, right? We see the chattering happening, going up and down, up and down, up and down, right? Now, let's go ahead and see if we can switch the control scheme now to use our hysteresis deadband. So let's use this guy down here. I like this one because actually we're going to see some fun things that you can actually see. Let me go ahead and reinitialize this. I need to run a script in the background to basically switch the controller. So now instead of using number 1, it's actually going to be passing in number 3 and use that as your control signal. And now if we run this simulation again, let me pull this up. This looks a lot cleaner, right? Look at this. This looks awesome. So again, if we zoom in to some regions of interest, let me see, maybe around here, you can see that, yep, even though it was noisy, right, and you can see that it's chattering up and down, up and down, up and down, we are not getting the chattering behavior. And again, that's because I chose a deadband size of, I think in this case it was 2 degrees. So you can think about a 2-degree deadband window around both the error and the control signal. So that's why we are not getting any of these problems, because this middle chart is looking at the error, and you can see that the deadband is up here at +2 and -2. So you can see that the error signal, the noise is not enough to bump you outside of that range. So that's what's going on. And in fact, to see that, maybe what might be fun is let's slow this simulation down and we can actually see what's going on in, quasi real time. Okay, so let me show you actually a couple of cool features in Simulink that's going to help us see what's going on. So one thing that might be nice is if you hit run, right, Simulink is going to try to simulate this as fast as possible. And with the simple model like this, it's just going to go lightning fast, right? In fact, I mean, you can see this. If we hit run, this sim is going to go, bam, it's done, right? So it's way too fast for me to see what's going on. One thing that's nice is if you come over here to the run button and instead click on this little drop down, you can enable what's called simulation pacing. So this is going to allow you to slow down the Simulink model so that you can kind of see what's going on. So you can make it way slower, way faster, but this is basically how we're going to allocate simulation time versus real world time. So I'm going to make this 10 so that basically 1 second in real life is 10 seconds in simulation time. So if I run this again, let me see if I can put this graph over here. Now if you run this, you see it's a lot slower, right? Now you can actually see what's going on. So we can see we're heating up, we're heating up, we're heating up, and now we're doing probably something. You can see the controllers flipping on and off. Let me do one more thing so to make this even cooler so we can even see what's going on. If you come into the controller, let's go down here and double click on the chart. In here, I would like to see Simulink can actually show you what state is it in. You can animate how this goes along. You can see when these events occur. To do that, we're going to come here on this animation speed. And I'm going to change this to, let's change it to slow, just so we can see everything going all at once. And now, let me see if I can put these on two parts of the screen. Maybe I'll put the scope on one side, and we'll put this on the other side. Okay, now, let me see if I can arrange this. Okay, now I think we should all be set up. So now, let me just double check. Yep, simulation pacing is set up. So, two things are happening now. We're going to slow the simulation down so we can see what's happening, and we're going to animate and watch what happens on the Stateflow or the finite state machine side. So now when I click run, notice it's got the little icon on top, so it shows that it's going to be a paced simulation, not a full speed simulation. So now when I hit run, we're going to go slow, and now check this out. Okay, now we're too cold. Oops, wait a second, sorry, where are we? Oh, no, sorry. Right now, we haven't hit the, we didn't introduce a step response. Okay, now we said heat up, heat up, heat up. So now it's too cold, it's heating up, heating up, heating up, heating up. Now, aha, it's going to hit the deadband. We're inside the deadband. Oh, and look, the noise, it pops you in and outside of this deadband, but again, it doesn't matter because it's at G equals 1, right? And now we finally get to the other side of the deadband, and again, we're out here, we're out here, we're out here, but again, you're chattering back and forth between this G equals 0, so again, it's not mattering. And now you can see we're too cold, or sorry, too hot, right? And now you can see how this works. This is actually really cool, isn't it? You can see exactly what's going on. You can watch the signals over here. You can see how the controller is responding. And you can see it's taking really slow steps because I think the noise, you can see right now, the noise is chattering us back and forth. So it's actually giving a slow animation. So you can see the clock, it's actually going way slower than we thought because it's intelligently slowing down the sim so you can see what's happening. So you can see right now the noise is just chattering us outside. We're outside the deadband, we're inside the deadband, we're outside, we're inside, but it's here at the G equals 0, so it doesn't matter. Oh, and now we're on the other side. So it looks like we passed through the deadband, and now you can see we're coming up. Yep, now we're way too cold, and the noise is maybe chattering us inside and outside the way too cold and inside the deadband, but warming. But again, this doesn't matter that we're flip-flopping between these states so quickly, but because it just stays on, right? The controller's just on this entire time, so it's not going to matter until we get through the deadband, and now we're going to start progressing. At some point, I'm expecting it to just stay out here at the way too cold outside the deadband region, and at that point, we're going to sit there until we get all the way through, or excuse me, until we reach back. So, yeah, I think we're on our way. But I think you get the idea, right? So this is really fun that you can see what's going on and how this works. So, yeah, in the interest of time, maybe let's do this. And again, you should be able to flip-flop this on the fly. So we can change the animation speed and speed this up a little bit more quickly. So we can see, there we go. Yeah, so you can see it really flip-flopping. Flip, flop, flip, flop. It's kind of fun, huh? Maybe that might even be too fast for our, oh no, I can't grab it. It's not gonna let me do this. But I think everyone gets the point at this juncture. So great, let's let this sim run, and we'll come back to MATLAB and look at some other results. Okay, and maybe just one more thing I'll do. I won't run this live so you don't have to stare at it and watch it evolve, but I do want to prove to everyone that basically the Stateflow equivalent or this if-then-else statement, they're all equivalent. So I did run these sims offline, one using, well, basically just using those two different controllers. And you can see, here's the results. They lie right on top of each other. And as you can see, both situations fix the chattering as expected. Now, you might be asking yourself, okay, fine, if this or the Stateflow, both of these things are equivalent, right? It's both implementing this algorithm of having a bang-bang controller with a hysteresis deadband. I obviously like this better, so why don't we go with this for the rest of the discussion? But I'm sure you're asking yourself, okay, fine, what's the price we're paying for this, right? Obviously, this is great because it eliminates chatter, but we must be, right, there's no free lunch. You're paying something for this, right? And what you're actually paying is you're paying a little bit of a hit in performance if all we care about is looking at tracking. So to illustrate that, let me pull up another set of runs that I did offline so you don't have to watch me run these. So what this is this is the exact same scenario with the same bang with hysteresis deadband controller, but all I'm varying is the deadband size. So the red line has a deadband size of 2 degrees. The green line has a deadband size of a ½ degree. And finally, the blue line has a deadband size of 0.02 degrees. So I'm getting tighter and tighter deadbands, or smaller and smaller deadbands. You can see that what happens is, as your deadband gets bigger, you are actually just getting more over and undershoot, right? You're not able to track this. In this case, we're just trying to track a constant 40, whoopsie, sorry, I clicked on that accidentally. But you're not able to track this constant 45 as well as you might have been able to earlier, right? And that's kind of to be expected, right? Because this deadband, you're basically opening it up and you're not taking any action. You're not changing your control behavior inside the deadband. So you're going to pay that penalty. Now, what you get for that, though, is you get a little bit more robustness to noise. Now, in these three situations, you can clearly see that all three of them eliminate the chattering. So you definitely want the blue. So you want to have a small deadband. Now, the flip side to that discussion is there a problem with having a small deadband? Well, the problem with the small deadband is, what if you have a really noisy system, right? If you have so much noise that the noise actually bumps you on the either far side of the deadband, then you now have a slight problem. So let me show you another sim example of, I'm going to be still running this controller, but let's run it with a deadband which is too small for the noise of the signal. So what I mean by that is, let's make the signal worse. So I'm going to simulate having a junky, poor, cruddy sensor. So you can see this is way more noisy than we saw earlier, right? And now I'm going to have a deadband size of, I think it's just 1 degree. Yeah, 1 degree. What ends up happening, right, is you can see that at some of these situations, the noise actually jumps past the deadband size, right? So you can see we're trying to track 40 degrees. So the deadband positive number is here at 41. The negative number is at 39. And you can see right in some of these cases, let's zoom in a little bit, right? It's chattering past the far side of the deadband, which leads you to have actual chatter in the control. So again, no free lunch. You have to be intelligent and choose the size of your deadband relative to the sensor noise that you're expecting to experience, right? So you want that deadband to be a little bit bigger than the noise threshold is basically what you're gunning for, right? Okay, great. And lastly, I'm sure everyone is thinking, okay, this is all great, fine and dandy, but really you are just doing this with a nice simulation. Does this actually work in real life? is this going to actually be implementable? So let me just show you the real system. Okay, so here we are. Here's the real system, and what I mean by that is, again, we've got our Stateflow implementation, right? Here's our Bang Bang with Hysteresis Band controller, deadband controller, and now instead of having a simulation model, I'm actually going to send this to the Arduino and run this on the Arduino. So this is going to be an awesome test to see, hey, can I actually use the Simulink Support Package for Arduino Hardware? Does it support finite state machines and Stateflow charts? And basically, can I run this on the Arduino? So let me go set this up on the Arduino. I've got it all powered up over here. And now, let's go ahead and run this. All right, so I think I've got all my variables defined. So let's just go ahead and see if I can hit monitor and tune. And this is going to be awesome. If you give this a couple seconds, you're going to see that this is actually going to compile the Stateflow chart, push it up onto the Arduino board, and now the Arduino can be running the actual real temperature control experiment, all in closed loop, right? So we're going to see how this works. So again, we're going to give this a couple of seconds, and once this says success, that's going to be great because now we're actually having a reasonably complex control system now, all running on this tiny little Arduino Nano board. So let me go ahead and hit that button, and hopefully the diagnostics will pull up and you can hopefully see that it's actually working. It's going to be building the Stateflow chart. Here it is, compiling it, code compiled, and it's connecting to the Arduino Nano right now. This does take a couple of minutes. I wish this were a little faster, but it is what it is. We're going to do some data conversions, and then, check this out! This is now running on the actual Arduino right now, and it should be heating up. So here's our temperature, here's all of our data, and yeah, this is the controller's on. It should be warming up, and this is going to take a while. So in the interest of time, again, I ran this offline so you don't have to stare and watch this. I'm going to prematurely stop this, and let me load up the data from an actual run, and we can see how this looks. All right, so let me pull this up here, and here is the real data acquired from the real Arduino and actual system. And whoopsies, that's not a good grab. Let me try that again. But you can see this is looking awesome, right? This is basically doing what we want. It's fixing the chatter. It's got real data. We are running a Stateflow chart on an Arduino Nano, and things are looking great, right? This is not too shabby. Okay, the last thing I think we should maybe do is, I think I promised everyone I'd show you how to actually do, how to build this Stateflow chart. So let me do that right now. Okay, so the way to do that, let's do this. Let me open this up, and I'll put this on one side of the screen. Okay, this is what we're gunning for. So the way to do this is, let's go ahead and just start ourselves a brand new blank model. And again, I just want to show you this because we do have dedicated videos on Stateflow. So if you want more information, please check those out. But I just want to give everyone a quick crash course on this in case you want to build this yourself. You should be able to do that. So let's come over to our blank model. Come down here. You're going to have to find Stateflow down here. It's a separate toolbox. And you're going to want to grab what's called a chart. So let's grab and drag and drop that on. And this here is, let's call this our demo chart. Okay? And if you double click on this, you get this yellow background, and we can basically start drawing this picture. So to do that, you basically want to first grab what's called a state. So you click on this, drag and drop it, right? And this is, let's make it this top one. You're going to give it a name called Too Cold Outside Deadband. Okay, something like that. And again, you can drag and resize this as you like. Now, what we have to do is we have to define what is the system supposed to do as soon as you enter this state. So I'm going to say, upon entry, colon, you're going to make the output 1. G equals 1. Great. There you go. And now, let's just go and draw the rest of these states. So I can either use this again, or I'm going to right-click, drag, pull, and hold to drop another version of this block, and let's say this is now inside deadband and warming, right? And then drag again. Now we're going to make this one What are you now? You're too hot outside deadband. And again, now we got to change this to g equals 0. And then lastly, let's grab one of these guys. You are now, this is now inside deadband, but now you're cooling, right? So you're doing this and changes to g equals 0. Great. And then what we can do is we need to define these events that are going from one block to the other. So it's really quite easy. Just click and left click, grab, drag, pull, and connect. So it's just sort of like Simulink. Now here you have to define what is the event that's going to occur so that you can take this transition. So I'm going to say brace EC less than or equal to deadband size and brace, right? And then again, you can do the same thing. You can drag, whoops, I'm trying to, well, careful, there we go. Have a transition coming back, and same thing. You could say EC greater than deadband size. Great, so you're doing stuff like this. Now the only thing we have to do now is, if you notice, going up a level, let's go up a level over here, you see EC is an input, deadband size is an input, and G is an output. This thing right now doesn't have any inputs or outputs. So we're going to need to add inputs and outputs. It's a little bit different in Stateflow. So I'm just going to double click into here. Okay, so we're inside our chart. Come over here to modeling. Let me make this a little bit bigger. That might help us. Come over here to the Model Explorer. So I'm going to click up here. And now, let me see if I can put this on one side. I'll put our demonstration chart over here. Actually, you know what might be more helpful? Let's go up a level so we can see what happens live. Okay, so now you can see in the Model Explorer, it kind of shows you what's inside the demo chart, right? It's these 4 states that we had earlier. One thing we're going to want to do now is add inputs and outputs to this. So again, I'm going to click on demo chart up here, and then up here, there's this thing that says add data. So when you click on that, you get this dialog to come up. So this, when you, in name, I'm going to call this E_C. And the scope of this is actually going to be an input. So now, notice now EC becomes an input to this chart. That's perfect. Let's just repeat this again. I'm going to click data again. We also need deadband size to be an input. And there we go. That's there. And lastly, we need one more thing. We need the output. So I'm going to click on add data again. I'm going to say G is now the output of this block. Apply. There we go. And now we basically made our own version of this block over here that I was showing in the demo. So of course you're going to have to fill this out, complete it, but I think you hopefully get the idea at this point. So this is pretty great. You're going to be able to build your own deadband, bang bang controller with hysteresis deadband system now using some of these techniques. So yeah, with that being said, let's head back over to the board and talk about some closing points. All right, so that was pretty cool. Let's go ahead and just summarize what we talked about today. So what I think we just saw is that basically what you're going to do now is you're going to choose this deadband size to be a little bit larger than your noise magnitude, right? That will hopefully solve this chattering problem. So the pros of this control system is obviously, well, yeah, it solves this control/actuator chattering problem if you choose the deadband size correctly. The other nice thing about this is it's not terribly more complicated, right? And you actually don't need the plant dynamics, right? We still don't know how fast this plant responded, how slow it responded, right? It's pretty darn simple. It's a heuristic algorithm. We might want to put a very small asterisk to this. I don't know if this is a completely true statement, but you really don't need a lot of plant information. You do need a little bit of plant information, but for the most part, you don't need to understand its dynamics. Some of the cons of this system is, well, you're paying for this performance for the noise chattering solution by accepting a little bit more over and undershoot, right? You saw that as you make this deadband size larger, right? The system, it's by definition not going to be holding tracking a value within this deadband size, within this deadband, because you got to sweep completely through it before you take some additional action. So you have increased over and undershoot. It's also slightly more complex. Well, I don't know if I would even say slightly, right? We were trying to make this one little epsilon tweak on a simple if statement, and suddenly this blew up into like a finite state machine discussion, right? So it is definitely more complex. And the last one, which kind of relates to this asterisk, is that now your controller design, it's not completely decoupled from your plant. You actually have to have some information about the sensor performance, right? So the controller is going to have to be designed to target a specific plant. So you might have to think about that. But in the grand scheme of things, it's really not that bad. It's a reasonable algorithm. The performance is kind of questionable, but like I said, it gets you up and running quickly. So, that being said, this hopefully sets the stage for some of our future discussions where we might want to address some of these cons and maybe come up with more sophisticated control systems using things like a root locus technique or other types of design methods to synthesize more complicated controllers, which will hopefully address some of these issues. But I think this is a good place to leave it for today. I hope this was reasonable. I hope you enjoyed it. I hope you'll also consider hitting that like button or the subscribe button. Both really help with the algorithm, and it really does help me continue making these videos. Remember, the new videos come out every Monday, so I hope we'll be able to catch you at a future discussion and we can all learn something new together. Until then, I think I'm going to sign off. Thanks a lot. Talk to you later. Bye.